and I do this, that doesn't change anything about the thumb, so I don't really have to do this. If this is the first vector and the second vector is this way, my thumb is still that way. Doing this is not going to change the direction of the thumb. So just putting the 4 fingers in the direction of the first vector is enough. Now, if you don't want to use the hand, then which way would it be? Then you can take the first vector and spin it towards the second vector and see which way the screw advances, and then you can use that. But anyway, so magnetic fields. So I'll say the following. See, Isaac Newton taught us that gravitational fields are generated by what? Mass. Right? So Newton taught us that. Einstein, gave it a new interpretation, but let's not talk about it. But according to Newton's theory, gravitational fields are generated by objects with mass. Right? At the beginning of this course, we talked about electric fields. And what did we say are the sources of electric fields? Charges, electric charges. So electric charges generate electric fields. And, at the fundamental level, if there's one thing you should remember about electric fields is that if the charge is positive, the electric field generated by that charge is
outwards,
pointing away from the charge. And if the charge is negative, it will generate an electric field pointing towards the charge, correct? But there are magnetic fields in nature. And so, for a long time, people thought, well, electric fields are generated by electric charges, so magnetic fields are probably generated by magnetic charges. Well, it turns out that no one to this day has found a magnetic charge in nature. Maybe they exist, but as far as we know, they're nowhere to be found. They're hiding somewhere. So it turns out that, we don't say that magnetic fields are generated by magnetic charges. There's also a mathematical inconsistency between a couple of equations that, they're known as Maxwell's equations. And so, so if there are no magnetic charges in nature, what produces magnetic fields? Because the magnetic fields exist. So what people learned is that magnetic fields are generated by the same electric charges that generate electric fields, with the condition that they have to be moving. So if you have a proton, for example, and the proton is at rest, it's a charged particle, it only generates an electric field, pointing away from it. But if it's moving, as it moves, it's producing that electric field, but it is also producing something else, a magnetic field. So it turns out that magnetic fields are generated by moving electric charges. Electric charges with the condition that they're moving. Magnetic fields. Electric fields by electric charges, regardless of whether they're moving or at rest, it doesn't matter, right? The electric charges will always produce electric fields.
How come, like a horseshoe magnet, there's nothing about it that's moving, but it still generates something?
What is a magnet made of? Atoms. And the atoms have electrons going around the nuclei.
Oh, okay.
What happens is that, but at the same time, this box is not magnetic, right? It's also made up of atoms. So what happens is that in iron, for example, at room temperature, you could arrange so that the atoms interact with one another in such a way that they are like facing in the same direction. I'll talk about it. Like right now, for example, if you're an atom, and you're an atom, and you're an atom, and you're an atom, you're all interacting in such a way that you're all facing in the same direction. You're all facing towards the front of the room. Yes. That happens when the object is magnetic. But if you get up at the end of class and you start walking around, and then you're not magnetic anymore. So and I'll talk about that later on. So at room temperature, iron, nickel, cobalt are such that the atoms can interact with one another in a strong way so that they line up in certain directions. Okay? It's like the electrons, so and the magnetic properties of materials, have various sources. Sometimes the magnetic properties of a material have to do with the electrons going around the nuclei. Sometimes it has to do with the free electrons that are moving about the material. It's called ferromagnetic. Sometimes it has to do with the nucleus of the atom, how they line up with the other nuclei. So there are various, magnetism is a very, very complicated subject. And so, but the materials themselves are made up of atoms, right? And the atoms have electrons going around, the nuclei are jiggling, so there is motion and there are charged particles. What happens with most materials that are not magnetic is that those motions are random. And so essentially, one of the atoms, for example, produces a magnetic field pointing this way. But another atom that's moving randomly produces a magnetic field pointing that way. And another atom produces a magnetic field pointing this way. And if you average all of that, you end up with zero, because the motions are randomized. But you can arrange things, and we'll see how that happens later on. If I take a chunk of iron and I put it in a strong external magnetic field, suppose I generate a magnetic field that points this way, essentially what will happen is like the atoms over here will all interact with the external magnetic field, and they're all going to sort of be made to face in the direction of the magnetic field. So they're all going to line up, and then they'll produce a sizable magnetic field themselves. And the nice thing about it is that you can, or interesting thing about it is that you can remove that external magnetic field and then it'll stay magnetized because of the interactions between them. So usually when you grab a bar magnet and you hit it, you pound on it, then you agitate the atoms and you agitate them out of alignment, and it loses its magnetic properties. Or you take the chunk of magnetic material and you put it on fire, or some heat source, thermal energy, and that thermal energy will agitate the atoms out of alignment. So usually raising the temperature of a magnetic material will make it lose its magnetic properties, or striking it, hitting it, for example, it'll make it lose its magnetic properties. But let's focus on the charges themselves that are producing the magnetic field. Magnetic field, first of all, are produced by moving electric charges. What is the unit of magnetic field in the metric system? Tesla, like the car. Well, I should say like Nikola Tesla. Actually, it's actually somebody's last name. I'm sorry, Nikola. It's just that most of you know the car, but you don't know about him. So, but anyway, Tesla is the unit of magnetic field, and magnetic field is a vector. It's a vector quantity. They're like electric field, like magnetic fields. Right? Now, remember that we spent 2 chapters calculating electric fields. The very first chapter that we discussed in this class was chapter 21, and there we talked about the electric field generated by point charges and by charge distributions. We did a charged ring, we did a charged disk, finite line segment that was charged, and we found the electric field using k dq of r squared, and then we did an integral. But then in chapter 22, we learned a trick that allowed us to calculate electric fields in certain cases when there was enough symmetry and certain charge distributions, like a point charge, just one point charge, or if we had spheres, or if we had infinitely long wires, infinitely long cylinders, infinitely large sheets, and we call that trick Gauss's law. So we'll do the same thing with magnetism. We're going to start calculating magnetic fields using something equivalent or analogous, not equivalent, analogous to k dq over r squared and doing the integral. And then we're going to do that. And then we're going to learn another approach where we make use of symmetries and so on, like Gauss's law, where in just a couple of lines we can get magnetic fields. So there are problems where we can calculate magnetic fields very quickly in just a couple of lines, like we calculated electric fields in just a couple of lines using Gauss's law. But I'll start with the more general case, like we did with k dq over r squared and did integrals and so on. I'll start with that approach. And then instead of taking that long approach, in some cases we're going to use something analogous to Gauss's law. It's called Ampere's law. Ampere, the person whose last name is the unit of current. By the way, what is a current in a wire? It's just a whole bunch of electrons flowing, right? And what happens if we have electrons moving in some preferred direction? Well, they're going to create a magnetic field. So you might hear people say, oh, magnetic fields are produced by currents. Well, yeah. Electric currents will produce magnetic fields because an electric current is just a whole bunch of charged particles moving. Right? At the fundamental level, it's a moving charged particle. Well, if you have a bunch of them, yeah, they're all going to produce a magnetic field. So we wrote like Coulomb's law, like k dq over r squared for electric fields. Well, in the case of magnetic fields, it's known as the Biot-Savart law. So, and Biot-Savart, these are the last names of two people. And I don't know about Felix, but the other one sounds French to me, and maybe the other one is also French. But you can see when these people lived. These people lived a long time ago. So Biot-Savart is like, k dq over r squared. And what they said was this. They said that, we in chapter 21, we wrote the following. Suppose you have an object that has a net charge Q, and it's charged, right? And you want to know, what is the electric field here? What is the electric field there? So the approach was this. You say, I am going to divide all of this charge in this object into many infinitesimal charges, and you say, okay, I'm going to introduce an infinitesimal charge over here, and I'm going to call that dq. And then I'll calculate the distance from that dq to the point where I'm interested in calculating the electric field, and I'm going to call that r. And then if this is a positive charge, it'll generate an electric field over here pointing away from dq. And you call that electric field the E. And the strength of that electric field, the E, generated by this infinitesimal charge, dq, we wrote it like this. But then to calculate the total electric field, right, you have to calculate the electric field vector there due to all the dq's, which is, doing that integral, doing that sum. Right? So then and you can write this if you like unit vectors. And so E net, E total, is the integral of, it's the sum of all of these dE's. And so it would be k dq over r squared. Then just to write it in a general way, I'll write a unit vector r hat. So this was in chapter 21. We did these problems, right? So what we're going to do here is the following. In chapter 28, right, we're going to say, well, magnetic fields are generated by moving charges. Well, I'll think of the moving charges as a current. So suppose there's a wire. Suppose here's a wire, and the current in this wire is this way. Right? Suppose the current in the wire is that way. And I want to know, and suppose that wire is in the plane of the board. I want to know, what is the magnetic field here? Produced by this current in this wire. So what you say is this: I am going to break or up this wire into small segments of length dl, and the current in that little segment is I. And then I go from that segment to the field point, and this is R. And I choose a unit vector along the direction of R from the L, from where the current is, to the field point. So I'm going to choose this unit vector, R hat. And the magnetic field generated over here, by the current I in this little bit of length, infinitesimal length, the L, is given by mu naught. By the way, what is this? Remember that this Coulomb's constant can be written as 1 over 4 pi epsilon naught. So, I mean, I could have written this as 1 over 4 pi epsilon naught dq over r squared, like that, right? So, I can either express it in terms of Coulomb's constant or in terms of some electrical property of vacuum. So, this mu naught is to magnetism what epsilon naught is to electrostatics. So, it's just a constant. It's called the magnetic permeability of free space. So mu naught is the magnetic permeability of free space, of vacuum. Epsilon naught is the electric permittivity of free space. Oh, that is vacuum, right? So electric permittivity. The other one is magnetic permeability. Permeability, mu naught. Epsilon naught was, what is that? 8.85 times 10 to the minus 12 in the right units. And this one is 4 pi times 10 to the minus 7 in the right units. Anyway, it's just a constant of nature. So you divide that by 4 pi, and then you multiply by the current I. And then you take the cross product between this length, dl. It's a vector in the direction that the current is directed with r hat. And then you divide by r squared. So this is known as the Biot-Savart law. And then if you want to know the total magnetic field, B net, it would be the sum of all the B's, and that would be, mu naught I. Actually, mu naught I over 4 pi will be constant, and this would be the integral of dl cross r hat over r squared. So this, we did a few examples using that in chapter 21, and now we're going to do a few examples using something like this in chapter 28. Here we had the dot products and the cross products. Here we have a cross product, so we need to deal with that dl cross r hat. And I'll start with the easier examples and then move on. Okay? In a little complication, I'll do like 3 or 4 examples. And this is known as the Biot-Savart law. And somehow I think there are 2 letters in there for the, is it 2 A's, 2 B's, 2 something? No. So this is the expression that we use if the current is constant current. So I should say that, not changing, like 5 amps, 5 amps, 5 amps, 5 amps. That's called magnetostatics. This one is electrostatics. So I want to solve an example using this. Okay?
Magneto.
What's that?
The X-Men Magneto.
Magneto.
Or from X-Men.
Okay, so let's see, do I have examples here or do I cook my own? I guess I don't know. I wrote some examples. Okay, so I'll do a simpler one than the first one. So calculate the magnetic field generated on the axis of a circular current loop of radius A. The current is I, constant, right? Here it says at a distance x from the center of the loop. How about we do it first, not off on the axis, but at the center of the loop. So what if we have a ring, and I want to know the magnetic field right at the center of this ring with a constant current in it? Let's do that one first. And then we'll move off the center somewhere at a distance x from the center on the axis of the ring. Okay? So let's do that one first. So, should I call it extra example or just example? So, it's a ring of radius A. With constant current I. Okay. Calculate magnetic field B at the center of the ring. Okay. All right, so we have a ring like this. The radius is A. Which direction would you like the current to be in? Clockwise or counterclockwise?
Clockwise.
Clockwise? All right. So I'll make the current in the clockwise sense. Okay? All right. So what I'll do is this. I will begin with I go to the source, right? And I'm going to choose how about I choose the L over here, like this, infinitesimal. It's long. It looks long, but it's supposed to be infinitesimal. So that's the L. Now, why do I put it at this point pointing up and not down? Because the current at that point is up. So the L is a vector that points in the direction of the current. Right? And so I write dB. dB is what? dB is the magnetic field generated at the center by the current I in the L. So this current I in this length, the L, generates this magnetic field. And I'm going to consider the point at the center. So by the Beals of our law, this is equal to this constant. That's the current in the L. And then I have to take the cross product between the L and a unit vector r hat. Now, how did I define r hat? Do you remember how I defined the unit vector r hat? It's a vector of magnitude 1 pointing from the L towards the point that we're calculating the magnetic field. So, I'm calculating the magnetic field there. So r hat is this. And this distance is r, which will be, in this case, equal to the radius of the ray. Are we good? And I have to divide, of course, by r squared. That's the Beals of our law. So that's what I'm going to start with. Any questions? Right? Understand that I is the current. The L is a length along the wire where the current is in the direction of the current. R hat is a unit vector from the L where the current is to the field point where we're calculating the magnetic field. And R is the distance from the L to the field point. So I have that cross product over there. Let's calculate that using what we learned today. So I'll do this. But what is the L cross R hat? Well, how do we calculate the cross product? What are the rules? The L cross R hat is going to be a vector, right? Because it's a cross product. In which direction does that vector point? What is the direction of the cross product, the L cross R hat?
Into the page?
Into the page. So, 4 fingers up, right hand to the right. Right hand, palm of the right hand. 4 fingers up, palm to the right, my thumb goes into the page. So the magnetic field here is into the page. Or just go like the L and then screw would go into the page. Or I'm going to write into the board. You guys write into the page. I'm going to write into the board. So this is a vector whose direction is into the board. But you guys write into the page because you'll be writing on the page. It's actually interesting how I've given final exams. And guess what? People write into the board. It's what they write on the page. Because they were writing, I guess, into the board, because I was writing on the board. So to me, it's into the board, right? But you have a page that's horizontal because you're writing on it on a page that's I'm writing on a vertical wall, you're writing. You know what I mean. So anyway, it's into the board. You guys write on your paper into the page. Now, what is the magnitude of this? Well, it would be the magnitude of the first vector times the magnitude of r hat times the sine of the angle between the L and r hat. What is the angle between the vector the L and the vector r hat? 90 degrees, right? You can see it in my picture that that's 90 degrees. So I'm going to call the L just, the magnitude of the L, I just call it the L without the arrow. What is the magnitude of this unit vector r hat? 1, because it's a unit vector. And the sine of 90 is 1. So notice this is just the L, right? And this is into the board. Into the board. Into This is the L cross R hat. It's a vector whose magnitude is just the L and whose direction is into the board. Are we good?
So why is the R hat turned to a 1 again?
What does R hat represent?
A unit?
Why is it called unit?
1.
Because the magnitude is 1. Yes?
Yeah.
So this represents the magnitude of a unit vector. Right? And the question actually has the answer in it. The magnitude of a unit vector. So the magnitude is unity, 1. Like the color of a white horse. It's white. So, but good point, because, a lot of people, what is that? So remember what the definitions of a unit vector, what the definitions are, right? And then, okay, so I'm going to continue with my Biot-Savart law, right? So now I'm going to go like this. I'm going to say, okay, dB equals. Remember, this is just the magnetic field due to the current I in this length, the L. What we want is the magnetic field here due to the current all the way around the ring, right? So this will be mu naught I over 4 pi. And then the L cross R hat is just dl, and, well, the direction is into the board. Into the board, and then divided by R squared. But R, in this problem, it doesn't matter where I choose the L. By the way, what if I choose the L over here? What would be the direction of the L cross R hat? Now R hat would be this. What is the direction of the L cross R hat? Into the board. What if I choose the L over here? Now that would be done because the current over there would be done. But now R hat would be this. What is the direction of the L cross R hat? Into the board, right? And so what happens is that this is a really simple problem because all of these contributions point in the same direction. So what do I get if I add 2 plus 1 plus 7 plus 8 plus blah? They're all in the same direction. If I add vectors that point in the same direction, it's just the sum of all the magnitudes, right? And the direction is into the board. And it doesn't matter where I choose the L, the distance from the L to the center of the ring, which is where I'm calculating the magnetic field, all of those R's are equal to the radius A, right? So this is into the board. Now, this is the magnetic field at the center of the ring generated by the current in the L. What I want is the magnetic field at the center of the ring generated by the current in all of the L's. And they're all pointing in the same direction. So how do I do that sum?